a person that is most knowledgeable about it, and I would want to have Slawomir with me on stage.
Thanks, Nico.
Yes, I was browsing through your CV, and in telecommunications, we're used to a lot of acronyms. I feel we have like SMO, especially in Open RAN too, and I saw that since 2021 you are the coordinator of the 6G RIC, but I have a feeling it's sort of a false friend. So we're not talking about the RAN intelligent controller, are we?
Yes, indeed. We are not talking about a radio intelligent controller, but this was on the purpose. It is a play on words because and 6G RIC stands for 6G Research Innovation Cluster, and I'm pretty sure and convinced that 6G will be open, and we will be talking about open systems, and RIC will play a crucial role. So this was just the reason for this.
And I think that's a perfect segue, right, for you to start.
Okay, thanks. So 2 remarks. Basically, I am going to report about the results of 6G RIC, this big project I am coordinating. And then the second remark is I'm waiting for the first slide. I apologize to those who attended my talk yesterday. It's not the same talk, but there is some overlap. Sorry for this, but this is how the life is. So, can I have the first slide? Or maybe we can also continue with the second one. Okay, great. So 6G RIC, 6G Research Innovation Cluster. I think that compared to other sessions, it's a little bit science fiction. We are going to look in the future, and I will start some kind of information about the cluster. 6G RIC. It's the center of gravity is in Berlin, but it's a cluster or hub, one of the 4 hubs in Germany, working on fundamentals of 6G. So you can see we have partners from all over Germany, but as I said, the center of gravity is in Berlin, and in particular here in these rooms. It is funded at the moment with 70 million euros, and then here you can see key strategies of this hub, and the main focus is on development of key 6G technologies, but of course we would like also to evaluate, validate those technology based on some selected use cases. Okay, so first of all, I would like to say that we have a testbed and infrastructure, outdoor testbed and infrastructure. We rely on open source testbed. So far we have 1 macro base stations, and we equipped 5 street lamps with 5G technology. And then we are working on topics like O-RAN framework, virtualization, and so on. And the potential use cases are in the automotive, including, for example, complete street perception or autonomous driving, and so on. Okay, so we are also planning indoor test bed, and this is in the big room over there, where you at lunch. And here again, it is supposed to be open, based on open interface and O-RAN compatible. And then at the back of this room, there is we plan an integration lab where we also would like to integrate systems together with startups and SMEs. Because we are planning also to establish a startup incubator. I think that it will be also co-funded by the BMBF to support young companies and to work also with us. And then we will provide access to the devices we have, and they are sometimes very expensive. So that I think that that's a good offer. And also, we are planning collaboration with the Charité. It's the biggest hospital in Germany. So at the moment, we have one campus, 5G campus network here in Wedding, and I think that we will intensify this collaboration in the next year. So, okay, so what is 6G about? Usually people talk throughput increase, right? So we need higher data rates. There are some use cases. When we were writing this proposal, some people were talking about 1 terabit per second. I think that we are a little bit more conservative and then say, okay, 100 gigabit per second would be okay. And what I would like to point out with this slide is that if you want to have more throughput per area, then you have, these 3 dimensions at least. Either you can improve the spectral efficiency, you can have higher density or more bandwidth. But if you increase each of these factors, it means that, you will have to spend more energy. So higher spectral efficiency, there is an inherent trade-off between spectral efficiency and energy efficiency. Higher density means more hardware, so more energy consumed by hardware. And then if you go to higher frequencies where you have a lot of bandwidth, hardware components are not so efficient. So at the same time, we have this trend to virtualization. And then, of course, you get more flexibility, but at the cost of higher energy consumption. And then here I would like to point out that 95% of the processing is required by the DU. So virtualizing DU is very challenging. And we did it together with NVIDIA. We use GPUs as hardware accelerators. And then also implemented some machine learning-based algorithms for NORMA. And what I want to say here, emphasize, is that, of course, there is not only trade-off between throughput and energy efficiency, but in fact between throughput, energy efficiency, and delay. And this trade-off is even more pronounced if you go, if you virtualize things. So here the table shows that if you would like to satisfy some kind of 5G requirements on latency at the low layers, so you need definitely more computing power and or use processors that are more powerful, but then they, of course, consume also more energy. So what I want to say is that we follow the direction set by 5G towards 6G, definitely. But I think that we have to extend our design dimensions to include energy consumption. And then, of course, there is this hype about AI, ML. Yesterday I said that AI has a great potential, but it's not for free, right? So it consumes energy, you need to collect data. So that's why we have to talk about data acquisition, not only in the context of AI, but also in the context of semantic, for example, communication. And then network computing is also an important aspect, I think, because we will realize the idea of convergence of information and communications technologies, to process data close to where the data is needed. So moving data around costs a lot of energy. Good, so this is our approach to 6G, RIC, also 6G RIC approach to 6G. You can see areas, we call them technology innovation areas. And then we have sub-terahertz mobile access, so we go to higher frequencies. I will explain why. Then we have this intelligent reflecting surfaces, for example, to shape the environment by passive elements. I am not going to talk about this. I was talking about this yesterday. Then we have the idea of network as a sensor. So it means that you use the communication infrastructure not only to send bits from A to B for communication, but also to do some kind of sensing, radar sensing in particular. It could be localization, but I think that also you can use this for intrusion detection and other applications. Here, especially, we are interested in channel charting. Data acquisition, semantic communication, I will talk about this. Embedded security, it's mainly about post-quantum security combined with physical layer security to provide some kind of protection against attacks from quantum computers and quantum hardware. And then autonomous convergent networks is mainly about the impact of all these technologies on networking aspects in RAM. Okay, so sub-terahertz mobile access. We go to higher frequencies because there is a lot of bandwidth. But the main issue is about energy efficiency. I mentioned this at the beginning of my talk because components are not so energy efficient. And then we have, of course, high path attenuation. So that's why a key component or steerable beamforming antennas is a key component of sub-terahertz. And then we needed to overcome, this path attenuation to provide some reasonable, coverage at this frequency range. So here there is a simple calculation why we are doing this. If you want to increase throughput by factor 100, right? So you can see here some numbers for sub-6 GHz 5G new radio. So in fact, if you stay with the bandwidth of 100 megahertz, so you need, this multiplexing factor, you need instead of 16 streams per squared kilometer, 800 streams per squared kilometer. And then you could increase the spectral efficiency from 4 to 6 beats per second per hertz to 8 to 12 beats per second per hertz. Okay, so I think that this, for me, this looks like mission impossible. So that's why the approach could be you go to sub-terahertz 6G, and if you assume you have 30 gigahertz bandwidth, then it would be enough to have 16 streams per squared kilometer, and then very low spectral efficiency of 3 bit per second per hertz. Why I'm emphasizing this? Because low spectral efficiency is an opportunity to use simple hardware components, right? I will briefly explain this later. Good, so this is our approach. We have some kind of heterointegration of semiconductor technologies. We use modular hybrid phased arrays. And then what I would like to emphasize is analog technologies, for example, Rothman lenses to generate small, narrow beams. So we are not using full digital beamforming, which consumes a lot of energy. We try to study analog techniques to generate such narrow beams, and of course they are highly energy efficient. And then, as I said, if we use low spectral efficiency, this simplifies hardware, power amplifier, and AD-DC converters and so on. For example, because we have constant envelope, so we have a low peak to average power ratio, and this allows us to use, simple or cheaper power amplifiers. And then there is another interesting point. If you use, such narrow beams, this has a tremendous impact on the effective channel. And this is explained here. First of all, before I explain this, there is a small video, short video, because I have to say that we have narrow beams. Of course, if you have narrow beams, radiate only in one direction, and then if the objects move, so we need some kind of tracking, right? And this is, I hope that this works. This is illustrated. We have a demo with LG. So you can see here's waveform at 150 gigahertz, bandwidth 400 megahertz. And then here, I would like to point out how sensitive the thing is. That if the receiver moves, so we lose more or less the received power decreases. But then, of course, this receive power can be re-established by changing to another beam. This is done manually here, but of course in practical systems we need to do it automatically and very fast, right? So it includes tracking from objects and beam tracking and things like this. And then here, you know, even if you turn the transmitter away, then it's also leads to a loss in the power, and then you have to change the beams to restore, you know, the communication. So this is a key component we are also working on. So here I would like to explain narrow beams. So narrow beams are a big problem in wireless communication are multipath components, reflections at walls and things like this. So, but if you have a narrow beam, then you have a spatial filter, more or less, and then the paths are cancelled or killed. And then it means this was the basic idea. And then we thought about this and then said, okay, so the channel might be flat, very, very easy channel. And then we evaluated this, validated using indoor measurements and 160 gigahertz with Roder and Schwarz. And indeed, the channel is almost flat. So what does it mean? It means that you can use single carrier because the intersymbol interference is not so big problem. You don't have, you know, multipath components or delayed signals, so you don't need to, you don't get strong intersymbol interference. You can use single carrier, simple equalizer, similar to what we are using in our FDM, and then that's it. And then you can operate in low signal to low spectral efficiency regime to use simple hardware components. There is a paper about this, and then we had a demo at the ICC in Rome 2 weeks ago, and this is a picture of this demo. If you are interested, if you would like to have more information about this, please contact me. So the second topic is the semantic communication, right? So we are talking about energy consumption. There is a strong need for energy savings in wireless systems. And then we always talk about, communication part, the communication channel. And then of course, there is something, there is also, you know, the other word, or the other side of the word, which is, you know, the application word. And usually, by Shannon and Weaver, especially in 1949, they identify 3 problem levels. The technical problem, this is what we are focused right now. It's about transmitting one bit from A to B in as reliable as possible. We don't care about the content of the bit or how relevant the bit is to the application at hand. So then there is a semantic problem. The meaning conveyed by the transmitted symbols should accurately reflect the intention of the sender. And I think that Alex in Dresden 1 month ago was talking about the effectiveness problem. The conduct of the system in response to communications should be effective in accomplishing a desired task. You know, now I am not talking about applications, you know, if you have smartphones and then they communicate with a base station and compete for scarce resources. I am talking about, for example, about multi-agent systems with robots that cooperate for a common goal, right? So the task is to achieve a common goal, and then the communication should be effective with respect to this, to achieve this common goal. And then, and this can be proven, the amount of data to be transmitted to achieve this goal can be significantly reduced when compared to the case where you consider these 2 parties or 2 robots as independent agents competing for scarce resources. So, okay, this is a 6G rig viewpoint at the problem. So it's about data acquisition, especially in the context of robotics. If robots do something, there are times there is more need for communication, and then there is maybe no need for communication. It's called event-triggered communication. But I have the second video. And these are Segway robots. We are building 20 robots like this. They should collaborate and perform some task. Here in this case, the task is relatively simple. This is a Segway-like robot. It's an unstable system, right? And then they have to bend forward and pass under the crossbar, right? So the problem is such robots can be used in applications in logistics. So they can carry some things, and you don't know the dynamics of the system. So you don't know, how to choose input signal to have, what you are interested in. So that's why you have to learn this, more or less. So and here you have an example. This is just in collaboration with Professor Jörg Reich. Here, we have a cluster science of the intelligence. There is collective iterative learning control. Here they don't collaborate when learning. One robot learns aggressively, the second one conservatively. And you see now the green curve means that they collaborate, they can learn much faster to perform such tasks. This is, I think, illustrative example of goal-oriented communication, which is fundamentally different from the communication when you have several smartphones, transmitting data to a common, to a joint base station. Good, this is more or less the last slide. We want to also implement this using spiking neural networks because of energy efficiency, but if you are interested, you can also download this position paper or talk to us if you are interested in more information. Thank you very much for your attention.